In this video, we will examine competition between unimolecular and bimolecular reactions and substitution and elimination reactions. When we consider competition between different reactions, between different substitution and elimination reactions, this table or this diagram summarizes it. We can look at alkyl halide, shown here with X for halogen, and you can see that on the left, alkyl halide can undergo three paths, three possible reaction pathways, path A, B, or C. Path A is nucleophilic substitution reaction, SN2 reaction, so reaction with the nucleophile where nucleophile displaces the leaving group in a concerted reaction. Part B would be the other bimolecular reaction, which is E2 elimination. So bimolecular elimination, where base removes beta proton accompanied by loss of the leaving group to give corresponding alkene. Path C gives the corresponding carbocation. So that one is shown in the middle on the right. And then carbocation now has two possible pathways. It can react with a nucleophile. It can combine with a nucleophile to give product of nucleophilic substitution reaction. That would be SN1 reaction. Or it can react with the base to remove proton beta to carbocation, and that would be E1 elimination. Product is corresponding alkene. So various factors now affect the outcome of a particular reaction. First, leaving group itself actually has limited to no effect on the reaction mechanism. In general, leaving group affects reaction rate, but not much the reaction mechanism. So alkyl iodides, among the alkyl halides, alkyl iodides are by far the most reactive because iodine is the best leaving group. It makes the weakest bond to carbon, forms the weakest bond to carbon. Then alkyl bromides, and finally alkyl chlorides. Alkyl fluorides are by far the least reactive, and they are not leaving groups in most of the reactions. They are in fact only reasonable viable leaving group in an E2 elimination reaction. When we consider competition between different reactions, typically competition is not between substitution or elimination. Typically competition is first whether the reaction is unimolecular or bimolecular. So a particular reaction, depending on the conditions, will proceed either through unimolecular or bimolecular mechanism. And then once the mechanism is clear, then within that mechanism question is whether reaction is substitution or elimination. So first let's look at unimolecular reactions. So in unimolecular reactions, competition is between E1 and SN1 reaction. So an alkyl halide in a unimolecular reaction loses halogen to give intermediate carbocation. And then that carbocation can react in this case with water either as a nucleophile to give corresponding alcohol or with water as a base to give corresponding alkene. So in the first case reaction is SN1, in case reaction is E1. In case of bimolecular reactions, so of course now competition is between E2 and SN2 reactions. And in bimolecular reactions, the factors that affect reaction outcome are degree of substitution, that means degree of steric hindrance in the substrate and the base or nucleophile, reaction temperature, and nature of the base. First, let's examine the role of degree of substitution on bimolecular reactions. First, degree of substitution in substrate or steric hindrance in substrate. Primary substrates readily undergo SN2 reactions. At the same time, when it comes to E2 reactions, tertiary substrates react at fastest rate, then secondary, then primary. Since primary react the slowest in E2 reactions, while they react very fast in SN2 reactions, SN2 reaction mechanism will be favored, or basically default mechanism for primary substrates. So if there is primary substrate, we would expect it to react by SN2 reaction mechanism, unless we apply some special conditions, as you will see in a minute. On the other hand, tertiary substrates cannot undergo SN2 reactions, but they react under E2 reaction conditions in E2 eliminations at very fast rate. In fact, they are the best substrates for E2 eliminations. So for that reason, under bimolecular conditions, tertiary substrate, as shown in the second equation, will undergo E2 elimination. When it comes to steric hindrance in the base, let's look at primary substrate like bromoethane. Ordinary base that is not hindered, such like hydroxide, that is both strong base and strong nucleophile, will act as nucleophile and SN2 reaction will occur. That's in part because for primary substrates, SN2 reaction is favored, it's default reaction. So with primary substrates, strong base, strong nucleophile, species that is both strong base and strong nucleophile, like hydroxide, methoxide, ethoxide, will react by SN2 mechanism, and products will be corresponding substituted products. On the other hand, if we want to carry out an elimination reaction, we should use large sterically hindered base, because sterically hindered base is strong base, but it's not a nucleophile. As it is not nucleophile, nucleophilic substitution is not possible. So this is how we can get primary substrates to undergo E2 eliminations. We should use large sterically hindered base like T-butoxide, and then E2 elimination occurs. So in conclusion, sterically hindered base favors elimination, while smaller base, strong nucleophile, favors substitution. And temperature, when we consider temperature, role of temperature, high temperature favors an elimination reaction for several reasons, and one of the main reason is that reaction is endothermic. So thermodynamically, high temperature shifts equilibrium towards elimination reaction, while low temperature favors a substitution reaction. That comes from expression for change in free energy in the course of reaction. So first term enthalpy is favorable in case of SN2 reactions. And so if temperature is low, the T delta S factor is small compared to delta H compared to enthalpy. So T delta S factor is small, role of entropy is small, and so reactions are driven by enthalpy, and that means that SN2 reaction is favored. On the other hand, a change in enthalpy does not favor E2 elimination because change in enthalpy is positive. It's endothermic reaction. At high temperature, T delta S factor is much higher, much larger, and may overwhelm contribution from enthalpy factor. And in the course of an elimination, of course, number of particles increases, which means that entropy increases. So T delta S factor becomes larger at higher temperature. As T increases at higher temperature, that means role of entropy becomes more important. And at certain temperature, role of entropy will overwhelm or will become more important than role of enthalpy, and that will favor elimination reaction. What is high and what is low temperature may depend on particular reaction system, particular reactants. Nature of the base plays important role on whether reaction proceeds by E2 or SN2 reaction mechanism. So strong nucleophile favors SN2 reaction, while strong base favors an E2 reaction. Now, when it comes to nucleophilicity versus basicity, what is strong nucleophile and strong base? Nucleophilicity is related to how fast a nucleophile donates electron pair. So that's a kinetic effect. While basicity is related to ability of a base to form a bond to proton, where is acid-base equilibrium. So that's thermodynamic effect. When it comes to steric hindrance and its effect on basicity and nucleophilicity, tertiary butoxide is 100 times stronger base than methoxide, but methoxide is much stronger nucleophile than T-butoxide because of the steric hindrance in T-butoxide. So steric hindrance will make species very weak nucleophile or maybe non-nucleophilic at all, but at the same time it does not affect base strength, and in fact because of the electron donation from those large substituents, it may even increase base strength. So sterically hindered species could be very strong base but very weak nucleophile. Now, charge density also affects basicity or nucleophilicity. Strong bases have highly concentrated charge. They are small charged atoms like oxygen minus or nitrogen minus. While strong nucleophiles have less localized charge, so they are large atoms with or without charge like sulfur or iodine, bromine. Those would be strong nucleophiles. Basic and nucleophilic properties of various reagents are summarized in this table. So strong base and strong nucleophile is species that is charged and has relatively small atom that carries that charge. That would be something like oxygen atom or nitrogen atom. They are suitable for either substitution or elimination. So if those are reagents, then you have to consider degree of substitution, temperature, and solvent, because either substitution or elimination can occur with these reagents. But frequently, substitution is preferred. But that's not the rule, so you have to consider all of the factors. Now, strong base and weak nucleophile is species that is charged but hindered. So top one is something you have seen many times before, tertiary butoxide. Potassium tertiary butoxide is most commonly used. Bottom one is lithium diisopropyl amide. I don't think you encountered that before, but that's also commonly used strong base that is weak nucleophile. So two diisopropyl groups on nitrogen provide steric hindrance. Bases like these favor elimination reactions. Now, weak base and strong nucleophile obviously is a species that is not basic, but is strong nucleophile, and those are generally halide ions, chloride, bromide, and iodide. Fluoride does not belong in this class. Fluoride has a little bit different properties. And these reagents favor substitution reactions. Elimination reactions with these reagents would be very rare. Finally, if something is both weak base and weak nucleophile, and those are anions of oxoacids that contain more than 2 or more oxygens, like carboxylate anion, bisulfite anion, biphosphate anion. Those ions are used when we don't want to have either nucleophile or electrophile in a reaction, when we want spectator ion. So, for example, we want something to accompany proton or metal ion, and it's proton or metal ion that is important in a reaction. Then we use these species, so those are spectator ions and they do not cause any reactions. So they do not undergo substitution or elimination reactions. Here is a summary of substitution versus elimination reactions. If substrate is methyl, then the only possible reaction is SN2 reaction mechanism. Obviously, methyl cannot undergo beta elimination because methyl has only one carbon, and of course minimum of 2 carbons are needed to form a double bond, carbon-carbon double bond. SN1 reaction is not possible as methyl cation is unstable and it's not viable intermediate in SN1 reactions. Primary substrates predominantly undergo SN2 reactions unless the base is hindered. With hindered base, they undergo E2 eliminations. So with primary substrates, reaction mechanism is bimolecular. Default is SN2, unless base is hindered, then it's E2. Secondary substrates are by far the most complex. So reaction with strong nucleophile, strong base, that means in general charged one, mechanism is bimolecular. While weak nucleophile, weak base, when it is also a solvent, usually not charged obviously if it's solvent, then reaction mechanism is unimolecular. So under bimolecular conditions, the most important factor is nature of the nucleophile or base. Steric hindrance favors E2 eliminations, while otherwise SN2 reaction is favored. Under unimolecular conditions, the most important factor is the reaction temperature. At low temperature, SN1 reaction is favored, and at high temperature, E1. And also E2 reactions have experienced same effect of temperature. So E2 versus SN2, so high temperature will favor E2 reaction, while low temperature SN2 reaction. Tertiary substrates in reaction with strong nucleophile or strong base, which are bimolecular reaction conditions, react by E2 mechanism. Obviously SN2 is not possible, and since mechanism is bimolecular, then E1 or SN1 are not possible either. With weak nucleophile or weak base, those are unimolecular reaction conditions. And then the most important factor is the reaction temperature. At low temperature, reaction mechanism is SN1, substitution, and at high temperature, E1, of course, elimination. Finally, alkyl fluorides react only by E2 mechanism. Fluorine is very poor leaving group, and carbon-fluorine bond cannot be broken to give corresponding carbocation. So unimolecular reactions cannot occur, SN1 or E1. And due to strength of carbon-fluorine bond, fluorine cannot be displaced by a nucleophile. Not even strong nucleophile can displace fluorine. So for that reason, SN2 reaction is not possible. Now, E2 reaction involves attack on the neighboring proton, and fluorine only leaves after carbon beta carbon proton bond is already partially broken. So actually bond breaking occurs elsewhere in the molecule, and that forces carbon-fluorine bond to leave or to break. So for that reason, E2 reactions are possible. So if alkyl fluoride is a reagent, the only reaction mechanism that is possible is an E2 reaction mechanism. And finally, we are going to look at one application of elimination reactions, and that's preparation of alkynes. Alkynes are readily prepared by elimination of two equivalents of hydrogen halide from dihaloalkanes by suitable base. Those halides could be geminal as top example or vicinal as bottom example. All that is required is that we have hydrogen and halogen, in this case hydrogen and bromine, pairs on neighboring carbons, so that we have on one carbon halogen, alpha carbon, and on beta carbon hydrogen. And those pairs could be different carbons, as you can see in bottom example. What is alpha carbon is different for each of the two subsequent eliminations. With use of base, product is corresponding alkyne. Now, base that is used for reactions like these has to be a strong base. Typical base that is used is sodium amide. And to avoid rearrangements, reaction works actually the best on terminal dihalides, like 1,1-dibromopentane. Of course, we have to use two equivalents of sodium amide because two equivalents of hydrogen bromide are being eliminated. If we use weaker base, like potassium hydroxide or sodium hydroxide, and carry out reaction at room temperature, or use only one equivalent of sodium amide, then only mono-elimination occurs, elimination of one equivalent of hydrogen bromide. And then product is corresponding vinyl bromide. So after the first step, product is vinyl bromide. So if we want to prepare vinyl bromides, we can do so by using only one equivalent of sodium amide, or doing elimination with hydroxide at room temperature. If we use second equivalent of sodium amide, then second equivalent of sodium bromide eliminates to give corresponding alkyne. Alternatively, if we want to use hydroxide, then we have to carry out reaction at rather high temperature because hydroxides are weaker bases, weaker than amides, and we need more rigorous conditions. So temperature has to be 170 degrees Celsius, rather high temperature for the elimination of the second equivalent of hydrogen bromide with hydroxide. This completes our study of elimination reactions. Next, we are going to examine reactions of oxygen, nitrogen, and sulfur containing compounds.